one, and the last one we have for today is by Giri. And the topic he's going to speak on is technical overview of Kubernetes.
All right, thanks, guys. I'm going to give you a very brief technical overview of Kubernetes. My name is Giri. I'm an engineer at Gojek. I've been an active Kubernetes org member. Prior to Gojek, I helped building Pivotal Container Service with VMware, Google, and Pivotal. And right now, I'm building Kubernetes at Gojek with some friends in the team. So Kubernetes, how many of you have been using Kubernetes daily at Office? OK, 5%. How many of you at least have heard of Kubernetes? Perfect, because the guy before me mentioned about Kubernetes a bit, right? So Kubernetes was an evolution on top of Borg and Omega at Google. They donated it in CNCF, which is called Native Computing Foundation in the community, I think around 2014. So Kubernetes is a very powerful abstraction that abstracts application containers and homogeneous machine fleet. So what this means is application containers do not really care which machine the containers get deployed to, right? Whenever we have a machine remove, this means containers' view of the world is just there's less compute power in the cluster. Here's the very high overview of Kubernetes architecture. There's an API server that is exposed various functionalities of Kubernetes. It's just REST API server, which is backed by etcd. etcd is a distributed key value storage with rough consensus protocol. Then there's this thing called scheduler and control manager as well that schedules a thing called pod across the entire machines in the cluster, kubelet, and as well as kubeproxy. You can just open the documentation. I'm not going to go through each of this because it's just 5 minutes. I'm going to show you what does pod mean. So in Kubernetes world, pod is a collection of containers. What Kubernetes tries to do, it tries to decouple application, as well lifespan of application, as well as data in this case. So because containers are transient, right? Containers are always crashing, restarting, but we want to persist the data. That's why the lifespan of the volume is actually decoupled from the application running. The pod itself is actually sharing various namespaces, including network namespace, mount namespace, IPC namespace, and all. And one powerful thing in Kubernetes is a thing called label, which is a first-class citizen. That this gives us powerful capability to query and slice groupings, any objects inside Kubernetes cluster, not just pods. So labels, let's say we have four pods here, labeled with anything, front-end, production, and even my name here, Gi Kunkoro. What the powerful thing we can do here is we can query what are the pods running labeled with production here, which give me 3 pods. We can also query labeled with role backend here, which will give me 2 pods over here. So this label concept is also used by all the controllers inside Kubernetes cluster itself. I want to take a step back and would like to introduce you a design pattern called reconciliation pattern here, which is used everywhere inside Kubernetes, as well as probably other tools in DevOps world. In reconciliation pattern, we have desired state. We also have actual state. There's this thing called reconciliation loop, which tries to match actual state to the desired state. In the context of Kubernetes, let's say we want to have 2 pods in the desired state here. The reconciliation loop, we'll see that the actual world only has 1 pod, which is foo. So the reconciliation loop will have an action called create bar, which will create a bar pod in the actual world. So the difference between Kubernetes and other cluster manager is that Kubernetes makes sure that the pods are available. When pods crash, it tries to always makes it healthy. Same with delete. The action is delete whenever there's a mismatch between actual state and desired state. The reconciliation pattern is also the core thing in Kubernetes replication controller. With the labels, the replication control queries what are the pods for, in this case, with label backend and production. And then there's this n number that makes sure that this backend production pod is running with n numbers in the cluster. For instance, 3 pods, meaning there needs to be 3 pods running in the cluster. Whenever 1 pod dies, the reconciliation loop will make sure to bring up another pod to match the three numbers of the numbers. Then the last thing is services. Also uses reconciliation loop here. Whenever a new pod is being spawned, the IP tables or queue proxy inside the cluster always make sure that those pod is accessible with this static IP 1234. Okay, thank you.